Hello everyone. This question has been taken from Olympiad Pathfinder, Chapter 3, Multiple Choice Question number 12. The question says, a semicircular rigid cylindrical tube is placed on a horizontal floor. Two identical balls that loosely fit inside the tube are simultaneously released from the top of the tube. Each ball moves down the tube on either side. One on this side, one on this side. Which of the following statements best describe the total force of normal reaction between the tube and the floor? Normal reaction here. It decreases continually. A. B. It increases continually. C. It first decreases, acquires a minimum value, then increases. And D, the tube may leave the ground. Let us work on this problem. When the ball is released, the balls are released, one ball is going this way, one ball is going this way. Since the ball is identical, means mass, structure, everything is same, and this tube is symmetrical and there is no friction. So both the ball will be moving identically inside this groove of the cylindrical tube. So let us catch at any instant when the ball is here and other ball is here, its velocity is v. So what is happening here? Since the balls are moving in circular motion, it will experience a centrifugal force that will be mv square by r, where capital R is the radius of the arc of the cylinder tube. So because of this centrifugal force, ball will have a tendency to move outwards. But the outer ring of this cylindrical tube will not allow it to penetrate and pass through. So it will offer a force that is a normal reaction force N, exactly opposite to the centrifugal force as shown in this diagram. Another force acting is the weight of the ball, that is mg, small mg. Okay, we have considered small m the mass of the ball, each ball, and capital M as mass of the tube for our calculation. Here the free body diagram of the ball has been made. All the forces are shown. From here we can see on one ball, force along the normal direction is N and a component of the weight mg cos theta. So N plus mg cos theta, that will be equal to mv square by r. So this is equation number 2. We have taken it as. Now since the ball is coming from here and going downward, so it is losing its potential energy. And there is no dissipative force, means there is no friction force available. So energy of the ball will be conserved. So change in kinetic energy of each ball will be equal to the change in potential energy, because it is coming down, so it is losing its potential energy, and that is being converted to its kinetic energy. So since we have assumed that it has acquired a velocity v at this location, so we can write half mv square is it as the kinetic energy. That will be equal to initial potential energy of each ball was mg into r. R is the height from here to here, minus the potential energy at this location. So potential energy at this location is r is the radius, r cos theta is this one. So mgr cos theta will be the potential energy of each ball at this location. So mg capital R minus mgr cos theta will be your change in potential energy. So this is what has been written as, we have nomenclated as equation number 1. Here we have shown the free body diagram of the cylindrical tube. So from the Newton's third law, you know that tube is applying a normal reaction force on the ball in this direction. So ball will offer exactly in opposite direction and equal in magnitude in this direction. That has been shown here. Normal reaction by the ground to the tube has been nomenclated or shown as N subscript T over here. Mg, capital M into G, is the weight of the tube, which has been shown here. We have assumed that its center of mass of this is somewhere here, and from there it is acting downwards. From the symmetry, it will be on this line only. The center of mass will be on this line, because the construction of cylindrical tube is symmetrical about this axis. Now we will apply NLM on cylindrical tube in the vertical direction. So 2nt plus 2n cos theta is equal to mg. But from equation 2 and from equation 1, we will put the value of n and mv and v square, and upon simplifying we will be getting equation number 3. So this calculation you can do by yourself. N subscript t is equal to capital M into g by 2 plus m in small mg 3 cos square theta minus 2 cos theta, and this equation we have given in number 3. To check, in the question it is asking the behavior of normal reaction from the ground to the cylindrical tube, that is NT. To check the behavior of NT with respect to theta, to know how the NT is changing, we will differentiate equation with respect to theta and will equate to 0 to know the maximum or minimum value of NT. That is one of your choice given in the question. So we have differentiated it with respect to theta and equating it for 0. So we got two things. One is sine theta is equal to 0 or cos theta is equal to 1 by 3. But sine theta will be 0 at theta is equal to 0, means when the balls were at the top position, theta was 0. So we are interested in knowing when the cos theta is equal to 1 by 3 because it has started from theta is equal to 0. So we should be interested in cos theta is equal to 1 by 3. At this value of theta, either your normal reaction by the ground to the tube will be maximum or minimum. So how to know this? To know this further, what we will do, we will differentiate dnt by d theta one more time with respect to theta, means d2nt by d theta square. Upon differentiating, we are getting this. And we should put the cos theta a value of 1 by 3. So now putting this value, we came to know that d2n2 by nt by d theta square is greater than 0. Means at cos theta is equal to 1 by 3, the value of normal reaction offered by the ground to the tube will be minimum. So we can conclude from this that initially the normal reaction offered by the ground to the cylindrical tube will be maximum when the balls were stationary. Then it will gradually decrease till the ball reaches to an angle where cos theta is equal to 1 by 3. Where it will be minimum, then again it will start rising. So answer C will be one of your choice. So answer C is correct. Now, the tube may leave the ground if at any instant of angle theta in the range of 0 to cos inverse 1 by 3, the sum of the component of the normal reaction by the ball to the cylindrical tube exceeds its weight mg, the total weight mg. Why? Because when the normal reaction vertical component will be more than your weight of the cylindrical tube, the tube will leave the ground. An unbalanced force will be available to lift it up from the ground. So it may leave depending on this condition. So answer D is also correct because it is saying in may. So I hope you understood the concept. Any doubt, please do let me know through the comments. I will come back to clarify your doubts. Thank you.